Welcome everyone to the second part of the Illuminating Transients in Earth Processes plenary session. The three plenary speakers in the rest of this session, plenary session, will be the first three speakers, and then the last 40 minutes of the 2-hour block will be a community session on visions for future geophysics infrastructure. I did just want to mention, because this is really relevant to transients and also the morning session, the morning plenary speaker units in this session, and also some of the posters, that there is a short course that just got announced today on GNSS interferometric reflectometry. I put that into the chat. If anyone's interested to apply to that, it'll be held in October of this year. So welcome everyone. I will pass this over to William as the chair for this session. Thank you.
Thanks so much, Beth. So welcome back for those of you that joined us earlier this morning, and welcome to those that didn't have the chance. So we're going to be continuing the session on illuminating transients, as Beth just mentioned, and we're going to shift gears after this morning's talks from water mass loading and hydrologic effects. And we're going to be looking more at tectonics and within the crust. So just as a reminder, these are pre-recorded talks that are last about 20 minutes, and then we have 5 minutes for questions afterwards. And we'd like that everyone, if you have questions, to please use the chat on the Pathables website, not within the Zoom window. And the speakers can potentially answer those questions during the presentation, or also Maureen will help corral those questions afterwards. So I think without further ado, we can introduce the first talk, which is going to be given by Catherine Materna, who is a USGS Mendenhall Fellow. And the title of her talk is going to be Geodetic Deformation Transients on Plate Boundary Faults and in Geothermal Settings. And she's going to be talking to us about changes in plate coupling over short timescales in Northern California near the Mendocino triple junction, and I suppose also in a geothermal setting as well. So I will let Catherine take it away. Thanks so much.
Good afternoon. Thank you for the chance to speak at this meeting. I'd also like to thank my collaborators who are listed here. Today, I'd like to talk about deformation transients, why they're so important, and where we can find them. I'd like to talk about this by exploring two geodetic transients, one in a plate boundary setting and one in a geothermal setting. To start, I'd like to talk about what is a deformation transient. In my research, I term a deformation transient as an unexpected time-dependent signal in geodetic time series usually, such as GNSS or INSAR, and usually lasting a fair amount of time, from days to years. Examples of deformation transients might be afterslip and post-seismic relaxation, slow slip events, ETS events, and even hydrological loading events, such as an extreme drought or a large hurricane. Any of these are able to produce transient signals in the GPS. So why do these transients matter? They can be indicators of dynamic processes, such as fault creep, fault coupling, fluid flow, stress transfer, and more. These transients and the processes that they represent are important for understanding earthquake physics, such as earthquake triggering, nucleation, and the generation of aftershocks. When studying tectonic transients, it's important to remember that transients are firmly on the observational side of science, which means that very often they present more questions than answers. So hold that in mind as we go through the rest of the presentation. In today's talk, I'll focus on two specific tectonic transients from two different regions in California, one at the Mendocino triple junction and the second at the Salton Sea. I'll also explore the implications of each of these transients. So first, let's move to the Mendocino triple junction, a region in Northern California where the Pacific, the North American, and the Juan de Fuca plates interact. The triple junction is here. It's a seismically active and tectonically active area with reasonably good coverage of GNSS, continuous GNSS stations, as shown here. An important thing to note is that because one of the plate boundary faults is a subduction zone, there is a subduction interface underlying most of the North American plate here. When we were examining the time series from this part of the world, we were surprised to find evidence for a subtle transient in the time series. Here I'm showing the east and north components of GNSS stations. The time series are from the stations shown in blue, listed from south to north. And it's a little difficult to see the transient here when there's still, there are no trends in these time series, but there's still seasonal signals. So we removed those signals. We tried a number of ways, and it's a little easier to see the subtle transient here. What we observed was a time around the middle of this time series where the velocities seemed to be a little bit more positive in the east compared to the other times in this time series. And it was coherent, it seemed, among at least a dozen of these stations. So this is the transient that we began to investigate. The way we did this is we started by investigating some of these individual stations, and we noticed that the time series is characterized by piecewise linear segments separated by turning points. We also noticed that some of these turning points are located in time coincident with regional earthquakes. For example, a magnitude 6.8 here and a magnitude 6.6 here. These are earthquakes in the Gorda Plate. To quantify the velocity changes that we see in this time series, we took the velocity for different stations in this time period T3 and subtracted the velocity in T2. We also computed the velocity change from T4 minus T3. So we examined the way that transient developed spatially. When we look at the T3 minus T2 velocity for every station in the region, we see a consistent eastward increase in velocities following 2014. The velocity change is about 2 millimeters per year. So this is subtle, but it is consistent in this region of the world. In 2016, we can take the difference between the T4 velocity minus the T3 velocity, and we get this velocity change, also about 2 millimeters per year, generally directed westward. So these are spatially coherent patterns. We wanted to also look at the temporal consistency. So we quantified the turning point by looking for the point of maximum curvature and plotted the turning point here for each time series relative to the timing of the two earthquakes that we know took place in 2014 and 2016. So when we do this, we find that for many of the stations with large velocity changes, indicated by the large triangles, the turning point is within several months of the timing of the known earthquakes. It's difficult to identify the turning point at a more granular basis than several months because the velocity changes are small and there is some noise in the GPS time series. But what this plot shows is that within detection limitations, the turning points for many of these stations are consistent with the timing of the offshore earthquakes. Another thing that we can tell from these plots and from the spatial and temporal patterns is that these transients do not resemble normal after-slip and post-seismic relaxation from the two offshore earthquakes. So they are likely indicating some other physical process. We wanted to know something about that physical process, and what we do know is that the subduction interface lies beneath each of these stations. So we investigated whether changes in velocity on the plate interface could cause these changes, these coherent changes in station velocity. So we performed inversions, inverting the surface velocity change for a coupling change on the plate interface. We'll start with 2014, the velocity change from T3 minus T2, and the inversion results are shown here. We found that a region of coupling increase, a particular region located around 25 to 30 kilometers deep on the interface, could explain the surface velocity change data. It does make sense that coupling must increase in order to drive the stations to the east, because that's the direction of the convergence of the Juan de Fuca plate. The particular spot that is most active in this inversion for the coupling change is located in an interesting place. It is just up dip of the tremor producing region, as shown by the brown contours on this plot. That's fascinating because they're in between the region that produces slow slip and tremor and the shallow locked portion of the megathrust. There is thought to be a transition zone, sometimes referred to as the gap. And not much is known about what goes on in that region, but it is thought to have partial coupling. And it's interesting that we're observing a coupling change around that region. When we look at the T4 minus T3 velocity change, the inversion results suggest a coupling decrease, which does make sense to move the stations to the west. And most of that decrease is located in the same spot on the interface. So what we see here is evidence for coupling increase followed by a coupling decrease several years later, each of them around the time of offshore earthquakes. A recent study by Nguyen and Schmidt this year looked at the same GNSS time series and found similar results. Some of the interpretation of their results is a little bit different and uses the terminology of long-term slow slip events rather than coupling changes. But much of the interpretation is pretty similar. Even the patch of slip change just up dip of the tremor. It does make sense because a coupling increase or the end of a long-term slow slip event are sort of the same physical process. The difference just depends on what we define the background interseismic rate to be. And given that we only have 15 or so years of GNSS data, it makes sense that our definition of background rates stands to be improved with the collection of more data. Some interesting observations elsewhere in the world also suggest that coupling changes on megathrusts may take place. So here I'm showing two examples from Chile, one associated with the 2005 Tarapaca earthquake, where a GPS station changed its velocity, and another associated with the Iquique earthquake in 2014. This case here, presented in Hoffman et al. 2018, is actually quite similar to what we see in Mendocino. The earthquake is regional in distance. It's about 200 kilometers away. And after the earthquake, these stations to the south experienced an increase in eastward velocity. An increase in eastward velocity may indicate an increase in coupling at the time of the earthquake at a regional distance. So it's similar to what we found in Mendocino, interestingly. Finally, there was a recent paper by Malik et al. That suggests that in the Sunda megathrust in Indonesia, there was a slow slip event in the 1800s that lasted about 32 years. So taken together, these observations, plus ours as well, suggest that subduction zone coupling may actually change in complicated ways, even during the interseismic phase of the earthquake cycle. And this provides a really important motivation for continuing to study deformation transients. So next, I want to change gears and bring us to another location with tectonic transients, the Salton Sea at the southern end of the San Andreas Fault. This is a transtensional fluid-rich regime with multiple geothermal fields, as shown in this plot here. And in terms of transient behavior, fault creep is common on many of the major faults in this region. The GNSS data show transients as well. So here is a plot of the east, north, and vertical GNSS time series from this area, and there are many transients here. The dominant one is this large curving transient associated with the post-seismic relaxation from the 2010 El Mayor Cucapa earthquake. But there are other transients as well, and in order to study them, we have to remove some of the other transients that are present. To perform this analysis, we modeled the post-seismic signal from the El Mayor earthquake using Hines and Hetland 2016, using their model. And we also removed seasonal terms and we detrended the time series with the pre-earthquake slope. And when we performed this analysis on the time series, our results are shown here. We find that at 2 stations, there is an unusual transient in east, north, and vertical that shows uplift and a sort of rotating signal. It's easiest to see the combined signal from east and north by looking at it in map view and seeing the rotation. It's at P506 and P499 near the North Brawley geothermal field. And this transient takes place between 2010 and 2013. There have been several other observations or examples in the literature of people observing this transient, for example, in Heflin et al. 2020 and in Gualandi et al. 2020. Gualandi et al.'s paper is especially interesting because they use a technique called independent component analysis to separate the different transients that are present in the combined GNSS data. And they decompose it, and in the decomposition, they find there's one component called IC9, one component that's difficult to explain, but we think it's the same signal that we've identified in the time domain that we showed on the previous slide, because it has its strongest stations right next to the geothermal field, and it has a time development that emphasizes movement in 2010 through 2013. This transient is significant because it is not easy to model with slip on the faults that we know about. But the uplift and the proximity to the geothermal fields may indicate that migration of fluids through pathways in the crust could have something to do with this transient. However, there's a lot more research to do to understand what caused it. It's important to do this research because there was an earthquake swarm in 2012 at the North Brawley geothermal field that produced 2 magnitude 5 earthquakes, and it was right around the time that this transient was dying out. And so it's important to understand the relationship, if any, between this coherent motion at several nearby stations and any sort of slip or other physical process that might have been taking place. This transient also shows us that for multiple simultaneous transients, such as afterslip plus additional physical processes, it may be difficult to detect an individual transient. And so it's important to note that some tools like PCA and ICA can aid and help us in automatic detection. Finally, I'd like to point out that one of the most fun and rewarding aspects of researching transients has been that projects on transients can create new research projects, and those can be really well suited for working with undergraduate students. In our research on the Mendocino triple junction, we searched for interseismic velocities, and that effort led to the summer projects of 2 Berkeley students, Lucy Sando and Saeed Mohana. And Lucy's in particular turned into her thesis last year. Lucy used the interseismic velocities to come up with an interesting way of grouping and plotting strain rate tensors derived from GNSS velocities. It's been really great to see both of them move on to grad school now, and it's been rewarding to work with them. So to summarize, I'd like to leave everyone with the following few thoughts. The first is that transient phenomena can happen anywhere where active faults occur. Next, the search for geodetic transients is an important piece of research, and it continues to shed light on new physical processes in the Earth. As geodesists, we have useful tools in our toolkit for identifying and modeling transients, and these include stacking, seasonal correction techniques, PCA and ICA, and really any detection scheme that leverages temporal or spatial coherence. This is an active area of development, and I'm excited to see what comes out in the next few years in terms of new techniques that help us identify these kinds of transients. Next, I want to point out that projects identifying transients and characterizing transients, for example, using time domain information, are really well suited for engaging students in research. And lastly, I want to point out that in order for all these activities to take place, continuous GNSS monitoring is essential for all of the research that we do. So thank you, and I'm happy to take questions.
Terrific. Thanks, Catherine. That was a great talk, really intriguing stuff. We'll open it for questions, and there is one already in the chat that comes from David Shelley. So he says, very cool observations. And with regard to the subduction coupling changes, any ideas about possible physical mechanisms? So what should we be thinking about in terms of the physics? And he suggests that maybe transient reduction in interface fluid pressure by draining some fluid into the upper plate could potentially be one. And apropos to that, he asks if there were any small earthquakes above the interface that might have been triggered by a pulse of fluid release.
Yeah, that's a really good question. We have thought about that a little bit as well. And specifically about the mechanism that you suggested, it seems a bit speculative or exotic, but it's still something that we've been thinking about. Specifically, we investigated the question of when did these changes occur during the ETS cycle. So in that part of Mendocino, the episodic tremor and slip events occur approximately every 7 months. But there are some gaps in that. It's not every single 7 months. And it appears that one of the earthquakes that caused that seems to be associated with a coupling increase was early in the ETS cycle, and one of them was late in the ETS cycle. So there could be something about a time-dependent change in the pressure conditions on the interface. That's still very much something that we're looking into. And then about the second question, did we look to see if there were any small earthquakes above the interface? We have not seen any near the coupling change zone itself, but interestingly, there has been a work by Travis Alongi and others at Santa Cruz looking at a kind of intriguing cluster of earthquakes a little bit further afield that happened around that exact time.
Super interesting. Yeah, Susan Schwartz also pointed to that in the chat. Let's see, there's another question, and Beth has pointed out, I'll just remind everybody that if you would like to raise your hand and actually ask a question, you can do that too, so people should feel free to do that. I'll also just read the next one. A question from Elham Moslemi. My question about the first part of your talk in the California region is how many stations did you work with? And could you comment about the process through which you considered the station's depth?
I'm not quite sure about the station depth. We used the stations from the PBO network that had continuous data. So I mean, we applied our, removal of the non-transient signals, the trends and the seasonal components, to pretty much all the stations in the Western U.S. and then looked for velocity changes. This one became quite apparent, and it was visible in something like 10 to 15 stations.
Excellent. Joan Gomberg has asked a great question, which may be hard to answer, but we'll see. She points out that the change you inferred in the Mendocino case is very localized spatially, right? It's a small distance along the strike of the subduction zone. What might be special about that spot? Why there?
Yeah, we've asked ourselves the same question too, and working with Noel Bartlow, some of our discussions on this have included the thought of one, this is an edge, the edge of the plate. It has, it's near the southern end of the subducting slab. And second, it's characterized by a little bit of a flat slab in this location. That's not the case for most of the rest of the subduction zone. So those are interesting things that we've thought about, but we don't necessarily have a connection, say, physically to why that might be.
Interesting. Very cool. I'll maybe ask one more, and it might be a naive question, but I'll ask it anyway. And you touched on this a little bit when you briefly mentioned sort of automated methods for detecting and characterizing these transients. But as it is now, are these transients often kind of just like picked out visually by somebody who's looking at a time series and is like, oh, what's going on there? How does that detection work, and what are the prospects for more automated detection in the future?
Yeah, very much right now they're sort of observed visually, and we came across this well, it was Noelle came across this first because she was trying to identify the portion of the velocity field that's due to slow slip events and the portion that's due to inter-slow slip events. And she began to notice that the inter-slow slip event velocity was not constant. In performing this analysis, we also found a few other kind of unexpected changes in velocity. One of them around the Long Valley caldera that's been reported on in a paper by Emily Klein a few years ago. So there are transients in the data that may not necessarily be identified yet. And in terms of automatic detection, definitely there's prospects for doing that in the future. But this ties into what we were talking about in the previous sessions and in the previous talks in this exact session. A lot of the signals are stacked on top of other signals, including hydrologic signals. There's drought, for example, that we take into consideration when we look at transients, especially in the vertical component and especially in California. So we could find, a rich array of transients, but it may be difficult to identify them as tectonic just automatically.
Yeah, excellent. That's a really good point. And I think we're going to probably move on to the next talk now, but there are some additional interesting comments in the chat that I encourage everyone to catch up with. And along that line, there's one that's asking about how do you distinguish tectonic transients from other other signals such as like growth of vegetation. So let's maybe continue the convo in the chat. But thanks, Catherine, for a really great presentation.
Thanks.
I'll turn it back over to William and we'll move on to our next speaker.
Yeah, thanks so much, Catherine. Super interesting. So we're going to slowly transition to seismology after we've been on geodesy for the past few talks. And although I think Qingyu said that she's going to include some geodesy here. The speaker is Qingyu Wang, is a postdoc at MIT, and the title of her talk is Seismic Monitoring of Crustal Deformation. And she's going to be talking about how you can use ambient seismic noise in barometry to measure changes following different types of transients with crust, such as a seismic sequence following an earthquake. So I will then leave to Qingyu to get started. Thanks so much.
Beth, I'm not able to play it. Can you?
Just a sec. We'll see. Is it not, the video's not playing?
No. It's coming up in the wrong format.
Yes, it looks like it'll work. Just a sec. Let me go ahead and share.
Apologies.
Make sure I'm sharing the right thing. All right, look okay?
Yep.
Hello everyone, my name is Qingyu Wang. I'm a postdoc from MIT. Thank you very much for organizing the workshop and inviting me this talk. So today I'll be talking about how we track crustal deformation by monitoring seismic wave velocity changes. Together with seismic observations, I will also show some geodetic observations and how they correlate with each other in both spatial and temporal domains. To start, I would like to recall a long-standing question. When do earthquakes occur? We know that an idealized model includes a stress build-up period. Once the stress reaches the local strength, an earthquake occurs with a sudden stress release. Then there's a post-seismic period, and subsequently a new earthquake cycle begins. While realistically, there will be variable strength, loading rate, and stress drops. Therefore, on timescales, the interseismic period or the slip behavior is very locally dependent and unpredictable. So what can seismic monitoring contribute to this question? seismic velocity can actually reflect the elastic modulus. Therefore, we are able to track changes in mechanical properties in the crust from the information carried by seismic waves. So far, we have observed seismic velocity changes related to multiple aspects, with order differing from 10 to -6 to several percent. Some representative examples showing velocity changes related to different earthquakes due to the tectonic forces. There are also a real strain-related velocity variation from a volcano in Japan. Beyond the tectonic-related deformation, there's also groundwater-related velocity drop as a result of the increase in pore pressure, and some other environmental perturbations. They can also generate velocity changes. For example, tidal strain-related velocity variation in Japan. The velocity changes and strain differences show good correlation. Although studies are ambient seismic noise-based CUDA waves monitoring. So far, we have different methods and sources for tracking seismic wave velocity changes with different purposes. In terms of types of sources, there are both active and passive ones. I would like to highlight some new methods based on different types of waves. Using active sources from an airgun, Wang et al. Have tracked high temperature resolution of P and S waves velocity variation related to local thermoelasticity in Yunnan, China. Liu and Benzium, they use earthquake data to study the velocity changes related to the Ridgecrest earthquake. They can track and map velocity changes with a high temperature resolution using aftershock correlation. In our group, Brian et al. First validate the feasibility of using receiver functions, the event-based seismic interferometry, to do monitoring, with potential to quantify changes related to slow slip events. And for passive sources, there's also a rapid development on a new branch, train seismology. Wang et al. In recent years, they succeed in turning seismic noise generated by the train into a powerful seismic source to probe the crust at a few kilometers depth. This figure shows continuous P waves retrieved from train noise in San Jacinto fault zone. And the great advantage of using active sources is a high temperature resolution can be guaranteed. However, passive sources can provide continuity in time and space. It is non-destructive and low cost. All of those cases I've listed show great potential to follow the crustal deformation continuously and statistically. Noting that different types of waves sample different parts of the crust. So, in practical applications, we should consider proper waves and proper method to fit different apes. In the following talk, I will be focusing on a passive noise-based seismic monitoring from the principle to a comprehensive application in Japan. The principle of CUDA-based monitoring is the time derivative of cross-correlation of signals continuously recorded at station A and B yields Green's function between A and B with an amplitude factor. The correlation functions carries information on the medium where the waves pass through around the two correlation stations. Once the medium undergoes a change, the waveform and the velocity change too, we can measure the time difference between any couples of cross-correlations to characterize the local deformation, especially nearby the two stations. The measurements are usually done on the late arrivals CUDA waves. It is multiple scattered wave. It cancels out some defects from the non-homogeneous distribution of the noise sources. Theoretically, we can get a relatively stable phase shift accumulated with increasing of elapsed time if considering a homogeneous medium. And in terms of measurement method, there are two main categories. One is based on the waveform similarity. The other is direct phase shift measurement using different methods. So using CUDA views, I've made a passive CUDA application throughout Japan. I use a phase shift measurement called doublet and combined with an inversion in time domain. It is well known that Japanese islands are located in an active plate boundary zone, where four lithospheric plates converge on one another. Therefore, Japan has experienced considerable seismic and volcanic activities. The magnitude 9 2011 Tohoku earthquake related both co and co-seismic deformation has been widely discussed based on the geodetic observations. However, the mechanisms behind this are still diverse and intricate. So, motivated by all those previous studies, we start to monitor the seismic velocity changes in the whole Japan from 2008 to 2012. The first study is in 1 to 8 second period band. Results in this period band essentially sample the velocity changes within 8 kilometers at depth. I pick up some velocity changes at 4 different locations. As you see, there are some quick velocity drops with 4 main earthquakes listed here. All the quick co-seismic drops are followed by long-term logarithm recoveries. In addition to those earthquake-related velocity changes, some annual patterns have an order comparable to those earthquake-related velocity changes. Furthermore, the tendency of those annual patterns is very different from one station to another. These annual changes are called seasonal effects. The existence of seasonal effects prevents us from tracking the crustal deformation neatly, but the existence itself also has important physical meaning. Because seasonal effects are usually discussed with environmental factors such as precipitation and snow in geodetic fields. And we use this animation outline the annual velocity changes averaged over years without significant events. If we look at how the seasonal effects fluctuate, we can observe the amplitude of seasonal effects can reach 10 to minus 2%. There are two prominent anomalies in eastern Hokkaido and the Hokushu. We finally identified that snow loading and precipitation-induced pore pressure changes control the seasonal effect in eastern Hokkaido. More complicated contributors, including sea level changes in the Sea of Japan, dominate the seasonal signals along the western coast. The Hokushu can be fully explained by rainfall-induced pore pressure increase from each June and followed by a gradual recovery. So seasonal effects have apparent regional features. They are closely related to the local meteorological and oceanographical environment. Those seasonal effects can be not only identified from seismic velocity changes, but also from grace-measured gravity field represented by the equivalent water height, EWH, represented in centimeter. So in Hokkaido, where snow mainly controls the high EWH in snowy region, while the substantial precipitation governs the high value in Kyushu in summer. I plot the daily velocity variations and EWH with a 10-day temperature resolution together. The same shapes of seasonal patterns first ensure the seasonal velocity changes are indeed from physical properties changes. Both time theories show a clear negative correlation, except in eastern Hokkaido, where the velocity changes and EWH show a positive correlation. It means that when the snow depth is big, the velocity increases. So the velocity has been increased by snow loading effect. This approves our conclusion. And the rest regions are negatively plotted for changes in Kyushu. When the precipitation is intense, the EWH is positive, the velocity changes are negative. For the Japanese Alps region here, the two are not that correlated, but for Western coastal region, the two are very well negatively correlated. So the EWH may also strongly affected by the Sea of Japan. When the EWH is high, velocity tends to decrease, and vice versa. Except the comparison with Greece, GPS can provide the direct surface displacement with higher spatial and temporal resolution. Japan operates a dense continuous GPS network known as GeoNet. We make use of all the vertical recordings from more than 1,000 GeoNet stations in the same time period. Those blue triangles show stations' locations. Similar to Greece, GPS vertical components are also negatively and positively correlated to the seismic velocity changes. Except these seasonal patterns, AAKH show earthquake-related changes in both seismic velocity and vertical displacement. At DAKH, both of them have similar 2 years long-term trend. So by the time series study, we see a very good correlation between seismic and geodetic observations. But in order to neatly track the tectonic-related cluster deformation, we have to remove those seasonal effects. Therefore, we build a linear model to simulate the seasonal portions for all single stations based on local meteorological and oceanographical recordings. There are 3 examples showing the synthetic velocity changes in red and black for measurement. The red curve recovers well from those different seasonal effects. After removing the synthetic velocity changes from measurement, the blue residuals show random changes for station UWEH without earthquake. The minimum detectable velocity changes are down to 10 to -5. The Tokachi Oki earthquake-related velocity drop that was previously heightened by the seasonal effect has shown up after the correction. So clearly, the environmental effects correction can help better track a long-term tectonic-related crustal deformation. Suppose we come back to our primary goal, the crustal deformation. What can we learn from seismic velocity monitoring? We first applied tiltmeter measurement to do correlation, and then checked the seismic velocity changes based on the CODA wells, the routine passive well-based monitoring. So we study the velocity changes associated with 2011 magnitude 9 Toku Oki earthquake. In this study, we use 171 stations of tiltmeter and the co-sighted short period seismometer to do seismic monitoring in different period bands. Therefore, we can sample different depths. We observe both dynamic and static stress and strain-related velocity changes at different depths. For a short period in 1 to 7 seconds, velocity decrease concentrate in this area, not adjacent to the epicenter. This is comparable to the PGV map, which reflects the dynamic stress changes. The good similarity of the two maps suggests the seismic velocity changes at a short period are sensitive to changes of the medium due to shaking, likely related to the nonlinear behavior of the superficial and consolidated shallow layers. For a long period study, we found that the area of maximum velocity drop shifts to the northeast and is in a good agreement with the spatial distribution of coseismic static stream at a depth equal to 20 kilometers. This static strain is calculated using GPS data based on the layered structure, considering both post-seismic viscoelastic effect and afterslip by Fried et al. The different spatial distribution of velocity changes indicates differences in behaviors at different depths probed by our measurement. The first-order conclusion is that there are specific changes at depths different from those in shallow layers. So, to conclude, from what I introduced in both spatial temporal domains, we see the necessity of cross-disciplinary study and the efficiency of seismic wave velocity monitoring. I would like to raise two questions as an open summary of today's talk. The first one is, how can we better localize the velocity changes that we observed from monitoring? In the monitoring with CUDA waves, in collaboration with Dr. Van Dinther from France's lab, we are able to simulate CUDA kernels in a non-homogeneous medium. For example, when a high scattered fault exists, using Monte Carlo-based simulation, we are able to get a high-resolution CUDA wave sensitivity kernels changing with lapse time. This provides a basis for further better mapping changes. Another question is, going back to the original earthquake cycle problem, how can we contribute more locally based practical information based on seismic monitoring? In collaboration with Dr. Nagahara from Tohoku University, we conducted a statistical analysis of the velocity changes before and after seasonal effect correction. We found that the corrected signals are more in line with Gaussian distribution. Their contiles plots thus tend to be straighter after correction. This test provides more information for better quantify the earthquake cycles in the future. So, to improve the temporal and spatial resolution, integration of different methods and seismic sources is proposed. We glean information from seismic waves, geodetic measurements, and numerical experiments. Therefore, further interdisciplinary collaboration is indispensable for comprehensively interpreting the observed changes. That's all for my talk. Thank you very much for your attention. I'm happy to take any of your questions.
Terrific. Thanks, Jingyu. That was a really interesting talk. And I, as a seismologist who does not ever think about transients in my own, imaging, it's really very cool to see these examples of, velocity structure changes on transient timescales. So we'll open it up for questions. So you can put stuff in the chat or raise your hand. Let's see, Roland Bergman has a question. What can be done to further improve the depth variation of the seismic velocity changes? And I think you might be on mute.
Yes.
Yeah, sorry.
Thank you, Roland. Yeah, this is a very good question. Actually, the depth estimation is always crucial question for the locating of velocity changes. And what we are doing now, either using different types of waves, either using CUDA waves, the routine passive wave-based monitoring. So when going to the CUDA waves, we are now very well solved the 2D kernels, and also the 3D kernels is under construction, but I cannot provide more on the CODA-based depth, but using different waves, especially the direct waves, I think the depth restriction can be better restrained.
Excellent, thanks. Let's see, we have something from Walter Mooney. So in addition to comparing your results to PGV, to peak ground velocity, it might be useful to compare with the surface geology, since the effect you seek to explain is related to the near surface properties. I don't know if you have any comments on that.
Right. This is very interesting. Actually, like PGV, the seismic velocity changes is also very sensitive to like the sedimental basin or volcanic area. So whenever there's a different surface geology, we expect to see different velocity behaviors.
Yeah, interesting. Maybe just as a follow-up, I was thinking along somewhat of the similar lines as Walter. I was in a way almost surprised to see the really great spatial correlation between the PGV map and the velocity changes, given that it's a big area and there's different lithologies and different conditions. So sounds like an interesting area for future research, I guess. Let's see, so Maureen Denal has a comment. CODA waves are mostly scattered surface waves as soon as there is depth varying structure. So all we can do now is just a frequency depth sensitivity, and direct waves might be easier to deal with. So just a comment there. Yeah, go ahead. I don't know if you want to react.
Yeah, that's kind of compromise. If we use like a noise-based or earthquake-based direct wave construction, it might, the data, we might need more data to stable the result. In the using scatter waves, there's always more stable result. But there is compromise as the depth resolution is not as good as using direct waves.
Mm-hmm. All right, we're gonna have to leave it there, but thanks very much to Catherine and to Ching-Yu and to David and our speakers in the morning session as well. This was a fascinating session, so thanks guys. And thanks also to William, who is having internet issues, but who played a big role in putting together this session. So on that note, thanks everyone, and we will turn it over now for our community session next.